Okay, we talk about a lot of fixed angle. Okay, so now we talk about what are the trends, direction of the phase angle for poles and zeros. Is it going this? Is it going this way, or is it going this way? Okay, if it's this way is negative, if this way is positive. Okay, so in other words, you have a graph. Okay, in this case, this is the real and this is the imaginary axis. If it's going in this direction, it is negative. If it's going in this direction, it's positive. Okay, so with this concept, let's start off with the poles. Okay, so we have a very simple pole s plus 1. And then since we know that maybe I should use different color. Since we know that s is equal to j omega, so therefore j omega plus 1. J is the same thing, this is equal to this. Okay, s equals to j omega. And therefore in order to rearrange this, okay, I multiply by 1. Okay, this whole thing is actually 1. Okay, I'm just multiplying the conjugates. Okay, in order to make it a complex form. Okay, the reason later you will know why. But you make sure you remember this portion over here, trying to make that complex form. In the future, it might be useful, but you take note that this is a very key, important understanding that you should go and multiply the, the complex form. But there is a shortcut if you want to plot a table to plot Nyquist plot. Okay, but nonetheless, this is a long one, but later you'll know why. But just remember this first. Okay, so if I were to do that, minus j omega. Okay, so if I were to do that, later you omega plus 1 multiplied by minus j omega plus 1, right? This denominator will be multiplied. You have minus j omega square plus 1 square. Then j square is equals to minus 1, right? So therefore we have omega square plus 1, which is this form over here. And then the numerator is minus j omega plus 1, right? So I split it out into a real and an imaginary, right? So this is minus j omega, okay? And then this is 1 over, because if you were to multiply everything inside, you have minus j omega plus 1, omega square plus 1. Okay, so if you were to rearrange, right, for this one, you'll get this one over here. So I just want to split it out into real and, so this is real, this is imaginary, so what I do is hope I understand. So after which, this is the real, this is the imaginary. So we are curious of the phase angle, right? The phase angle is actually the angle over here. Okay, how under what frequency will it move slower? Okay, as you can see in the previous video, although I didn't write in terms of frequency, but as you know, there is a lag. Actually, this is a delay. Sorry, hold on. Okay, so phase angle is actually the lag. Okay, phase angle is actually the lag. The phase angle is to measure the lag itself, the delay. Okay, so as you can see, this is the input, and then this is the output. In this case, it's voltage to current. So you're pulling voltage to change the current, and yeah, but it's the same analogy. So let's continue first. Okay, you have this form over here. Okay, this is imaginary and this is real, and I actually put the numbers in. Okay, so my real number is actually 1 over omega square plus 1. So this is if I sub omega square equals to 0, I mean if I sub omega is equals to 0, okay, what I have is 1, right? Because 1 0 plus 1 is equals to 1, right? So therefore I have a value of 1 over here. Okay, and then if I were to sub in, since I sub in 0 over here, I have to sub in 0 over here, right? So therefore 0 divided by 0 plus 1 is still 0 ma. So it is somewhere over here lah. But nonetheless, I just want to say that there is an angle. Okay, if you put in different omega, you will have different magnitude. So let's say if you put in, let's say 3, right, this is 1 over 10, which is 0 0.1. In this case, it's 0 0.1 over here, right? If I sub in omega is equal to 3 lah. Okay, so 1 over 3 square, which is 9, right, plus 1 equals to 1 over 10. And then if I were to sub in omega to 3 also over here, we will have 3, and then 3 squared is 9, so in this case it's 10. So I have minus 3 over 10j, which is 0.3 j, right? Minus 0.3 j because there's a minus sign over here. So and if I varies omega, I will have a point at this point. Okay, so if I plot, typically I will plot a root locus out. Okay, but later I'll show you how this thing works. But this is typically the case. Okay, this is minus 0.3. Okay, and therefore to find the angle, simply you're just finding the magnitude first, and then you find the angle. Right? This is the key case I'm talking about. So in a more general form, okay, this is what we have over here, okay, and therefore you know that the angle itself can be calculated by opposite divided by adjacent, right? The tau so if you remember. So this is the tangent is equals to O opposite divided by adjacent. So if in our case, opposite is actually just opposite the angle, which is actually the imaginary one, which is in this case the imaginary value lah. So in this case is minus omega squared plus 1. Okay, so this is the opposite. Okay, this is the imaginary one, and then adjacent is just simply the real axis, right? It's over here, this real axis. So that's why I take this value over here and put it over here. So this is opposite, then this is adjacent, and this is the real. This is the imaginary, this is the real. Okay, so imaginary is over here, the imaginary opposite, and then real and adjacent. So if I were to do that, okay, what do I have? If I were to cancel, because they are in the same form, okay, to cancel off. If you going, yeah, you need to know, okay, you need to know that this, if you have this type of form, okay, you can cancel straight away. Okay, so therefore I have minus omega divided by 1, which is equals to minus omega. So in this case, our phase angle is actually equals to minus tangent inverse omega. Okay, for the case of s plus 1. Okay, for the pose. So what information can we get from all this? Okay, so let me take a look. Let us take a look. Okay, so perhaps with this, since I know that the phase angle is equals to minus tangent, and I have a magnitude of 1 square plus omega square, because as you can see, the magnitude itself. Okay, so if let's say you want to take a magnitude, okay, magnitude is just taking the real, okay, times real square. So the hypotenuse, as you know, it's x square is equals to c square is equals to x square plus y square. So in this case, the x square is actually the r, the real axis plus the imaginary square. So with this concept, okay, this is just the trigonometry rule. Okay, with this concept, let's do the magnitude over here. Okay, if you imagine this is the real, right? So this is the real square, and then this portion over here it's the the imaginary square. Okay, so with this said, let's do a table, and then we can actually plot our root locus. Okay, so hold on a while. So after we get a magnitude, we can actually plot a table. Okay, so this is the tangent, the phi angle, okay, minus. So this is the phi angle, okay, the angle that I've shown earlier over here. Okay, and then if you were to sub in your omega now, okay, so this is the omega line. So if I sub in 0 into this equation, okay, this is 0, and then 1 divided by 1 is actually 1. 1 plus 0 divided by anything is 0. So 1 square root is also 1, so therefore we have a 1 over here. So in any case, in other words, this is 1 square plus 0 square is equals to 1 is equals to 1. right? So this is why I have it over here, right? And then since my omega is equals to 0, therefore tangent inverse of any tangent inverse 0 is actually 0 lah. If you don't believe, you take your calculator and type. Okay, and then if I sub in infinity, okay, into this equation now, okay, what do I have? I have 1 divided by infinity, because this is negligible already, only this. So 1 over is actually 0, 0 square plus infinity divided by infinity square. So therefore, it's also 1 over infinity. Okay, it's just the law itself. You cancel, you have 1 over infinity, right? So therefore, this is also 0. So therefore, everything is equal to 0, and we have 0 over here. And if it's omega, okay, if omega is infinity and tangent inverse infinity, okay, if tangent inverse of any big numbers will get minus 90 degrees. Okay, so therefore we have this thing. And if you were to take a look in the root locus, okay, at if my omega frequency is equals to 0, right, my magnitude is equals to 1, which in this case, if I take a look, okay, let's click, okay, click. I was wondering if I can click it. Hold on, yeah. So as you can see, if my omega frequency is equal to 0, right, in radians per second, my real axis is 1, which is the magnitude. Okay, the imaginary axis is 0. And then if I were to sweep all across, I plot, okay, as you can see, the frequency increases. So as my frequency increase along this line, this contour, okay, 0.03, as you can see, the values increases throughout. As you can see, it goes all the way, frequency radian per second, goes from this value to all the way here. As you go to infinity, like let's say this is infinity, as you can see, this is 5e bar 16. As you can see, once you reach here, they actually do a lot of they actually increase the frequency quite a lot. So when you reach here, you actually have a very big number, okay, 5 to the power of 16. Imagine it's that big, which is infinity lah. So in this case, as you can see, the real is also infinity. And the real is 0 because 1.22 e negative 33. So exponential to the negative is very, very, very small. So then imaginary is minus 2e, which is also very small because exponential, as you can see, if I were to show you, 9 to the power of negative, so 5 to the power of negative big number. Give that input, good job. Okay, I use the calculator over here, 5 to the power of negative. I just put any number to the negative, okay. As you can see, we are going to 0. And this is why, this is it lah, So this proves that the real and imaginary are at 0. So it's back to the origin. So it goes one round back to the origin. This is when you plot frequency in the positive. Okay, these are all positive values. So let's say if I were to show negative, so this is actually the reflection. So you can see these are all negative reading. So if when you're plotting from so typically you will be plotting from 0 to minus infinity in this case. Okay, so this is going in this manner. So when you're 0, you have certain frequency, and then you plot, and then it goes all the way. As you can see, your frequency is going. Sorry. This is when your frequency is getting smaller and smaller. And as you can see, minus 0.68. And if you were to plot from minus infinity to 0 lah. Okay, in this case it's negative. So this graph over here is negative. So when you plot frequency from 0, frequency equals to 0 over here, and you plot all the way to infinity, minus infinity, what you have is actually you're back to the origin also. So this is a very key concept. Actually, I haven't finished yet. Okay, I just want to summarize the part first, and then I will explain to you. This is the shortcut table that we will be always using. Okay, these are the shortcut method I will always using. Okay, the form where you, okay, so typically we have a pole at first, right? And then we sub in s equals to j omega over here, and then I do a complex conjugate. Okay, this is actually 1. Okay, minus j omega plus 1 divided by, so this is 1. Okay, this is 1. And then I just rearrange only, simply I just rearrange this portion. I get a real and an imaginary axis over here. Okay, and then I plot the magnitude. Okay, as you can see, it's just real square times real is a trigonometry rule, as you can see. Okay, so this portion is this portion here. You just sub in real square plus imaginary square, you get this portion over here, right? And then the phase angle I also derive. I sub in the opposite over adjacent. Okay, and then I get that my phase angle is as a negative tangent omega. Yeah. So what do you conclude over here? Okay, so we can conclude that the magnitude and the phase angle is all we need in plotting the root locus, right? As you can see, we are plotting as frequency increases. You can actually plot the point, and then you can just plot it out. Okay, so the critical point is actually to change this to this, and then the rest later I'll show you there's a shortcut. Okay, and the shortcut is actually this table over here. Okay, instead of multiplying the complex conjugate, okay, instead of do this complex stuff over here, what I did was I actually just do in terms of this. As you can see, this is equals to this. Okay, because simply this is actually 1, right? But the information that this piece contains is quite a lot compared to this. So this is just one small piece. If you were to open up, it becomes this big piece over here. In other words, this big piece over here is equals to this one. They are the same. They are the same thing. Okay. So as you can see, if they are the same thing, you can actually use the same method to solve for it. Okay. The purpose of me doing all this long chunk of stuff and then proving is just to prove that this is the thing. Okay, to make a very strong stand. Okay. And therefore if you want to in exams, if you want to find magnitude, okay, you can straight away use this one, and then this is actually imaginary already, and this is real. So real square plus imaginary square omega. Nonetheless you have to keep the so nonetheless it's 1 divided by this is the thing. So in this case, this is why I have since the real is actually 1 square plus, so the take note one thing, okay, the j will be removed. Okay, j is just stating that this is imaginary. When you're talking about um how much j you increase, okay, it's just the omega itself, so it's just omega square plus 1 square. Same as this thing lah, okay. Do you see any j over here? No, right? If I were to multiply j square, it's yeah. Nonetheless, I don't want to complicate things, but make sure that you know how to translate. Okay, so this is why this is a very critical point. And therefore, if you were to take a look, this is the magnitude itself, and then this is the angle that I proved to you. You can straight away use. Just take note that poles, okay, for poles is always negative tangent. Okay, and then now you see the values. If I plug in my omega equals to 0, I have 1 0. If I plug in omega equals to infinity, you have 0 and minus infinity, which is the totally same thing as this table over here. So this table can give us the same answer of in this table. That's all I just want to say. This is a full scale proof. Okay, and therefore as you can see, this will be easier. Nonetheless, as I say, please remember the conjugate part. Okay, please remember this, how you do this. In the future, we'll still get back to this and try to solve for certain stuff. In the future, I'll talk about it. But in this case, let's just use this first. Okay, use this in your plotting of the root locus, and then remember this in the future. That's all I want to say. And then So I have a little time, although it's a very long video. I just want to prove for the zeros part. Okay, let's say we have an equation for only 0, s plus 1 only. Previously we talked about poles, which is 1 over. Okay, so now we talk about zeros, numerator. And if you were to sub in the same thing, okay, s equals to g omega s plus. So this is s equals to g omega, so therefore I have this over here. G omega plus 1. And then you have a complex number straight away. Okay, instead of this one, you have a complex number in divided. So really, if you have a divide, okay, something like divide, you make sure you multiply the conjugate inside lah. Okay. But nonetheless, repeat again, this is actually 1. Okay, so you didn't change any equation. Okay, and then since we have this, we can actually plot the real and imaginary plot. Okay, as you can see, the real axis is actually this one, and this is magnitude 1. Okay, is 1. And then the omega varies as it increases. Okay, so as poles increase, so as this omega increases, then you have a certain phase angle. As similarly, you have opposite. So this is opposite, and this is adjacent, and therefore tangent inverse opposite divided by adjacent, you have equals to omega. Imaginary is actually omega, right? Divided by 1, which is the real axis. Magnitude of 1, you have what we have over here, positive tangent. And then magnitude is equal to omega squared plus 1 square is just a trigonometry rule. R square, so this is R square plus imaginary square. Got it. So this is the magnitude itself. And then if you were to take a look in the root locus for the zeros, okay. And then for the zeros, the Nyquist plot is actually this one. Interesting, right? So if you were to compare back, if let's say I compare the G of S is actually the zeros and T of S is the poles. Okay, now we compare. You can see this is the system. This one is T of S. Okay, this is T of S, and this is G of S. Right, this is G of S. So this is the poles. I mean, this is the zeros, and this is the poles. So as you can see, the difference is that for poles for poles is circulating, and then for zeros is moving upwards. But however, the angles are all the same. I actually plot a table now. So the magnitude is just as I mentioned earlier, and the phase angle is this one. And if I plot 0, okay, 0 plus 1 is actually 1. Square root 1 is also 1. So tangent inverse 0 is actually 0. And then infinity, you will definitely get back infinity, okay? Infinity square, this is negligible. So imaginary square root is come back to infinity. And then tangent inverse infinity is actually 90 degrees. And therefore, if you don't believe, let me take a look. Okay, so if I were to tangent inverse 90, you see I have about, what am I doing? Sorry, tangent inverse, arctangent a lot, a big number infinity, you have 90 degrees over here. So it's just to prove. So therefore, as you can see, just to summarize, the Nyquist plot for a pole is this orange color. As gradient increases from okay from as the frequency increases for pole, it will move towards the origin. As a frequency increase from a 0, okay, it will go to the infinity line. Okay, this is only for if you are very varying the frequency in terms of 0 to infinity. Okay, from 0 to infinity. So if I were to include the negative zone, as you can see, you have a reflection. So this is the Nyquist plot for a pole. This line is the Nyquist plot for a 0. So I hope I clear all the doubts. And make sure you go and remember the method of doing this. Okay, don't go and do this big chunk over here. Okay, this is when you have a 1 over g omega plus 1, you have to use conjugate. In the future I'll talk about it. But remember this one, use this one. Okay, and then yeah. So in the next video I will actually talk about the stability theorem, okay, some sort of stuff, and then I'll just move on to it. So I'll see you in the next video. Bye bye.